regardless of the process that you use, you will have like some common steps. Now, typical wafer processing steps includes so we go through each of these before we go into detail. I'll highlight the high level topics. So this is in order. So we have to do substrate material growth, wafer production, surface layers, photolithography, wafer thinning, substrate vias, backface metal, chip separation, and quality assurance. Now the last, quality assurance, can happen throughout any of these steps. Now we'll go through substrate material growth. So when you make say in your case gas wafer, there's a way that it is made, right? So what we are trying to do is in the substrate material growth, we actually grow that wafer. It doesn't come as a wafer, it comes as a ingot, like once you made it, it'll come as like an ingot like this. We'll go into a bit more detail on that. So we have to grow the material from a single crystal boule of the semiconductor. So there are mainly two methods that you can make these semiconductors. There's actually more than two, but we'll focus on two. So one is called liquid encapsulated Krasky method. I'm not sure that I pronounced it properly, but it's called ELEC method, right? So that's the figure on the top. So what you do is you have a molten material, and then you dip a seed crystal, and then you do a temperature gradient, and around that seed crystal, the wafer is going to grow like this. This is going to grow, and it will end up something like, once you cool it down, it will end up something like this ingot, right? So there's a lot of videos that you can watch how these things are made. It's quite interesting. The processing technology, so if you come into semiconductor field, so we are mainly designers, right? The separate total job field just on semiconductor processing. So this is just a glimpse of what it is. And we don't do it here, but we normally, if you are interested in this type of work, like understanding this stuff, experimenting with this, there's jobs with this fabs, like fabrication facilities. So example, Wing Semiconductors, BAE Systems, and there's UMS. There's a lot of companies that do just semiconductors, like wafers. So they, depending on what their preferred technology, they might use a ELEC method, or they might use this vertical gradient freeze VGF method. And the VGF method, so there's all molten, and the seed crystal at the bottom. So in the top one, ELEC method, you actually grow the ingot out from that this structure. So it'll come out something like here. Can't see my mouse, right? You can't, when I say here. Okay, so maybe I should. So this is the ELEC method. So once you actually pull this out, it will turn out to be something similar to this. So we call this the ingot. So similar ingot, you can get it from the VGF method. So if you are interested, you can read more. This is just to give you an idea that there are different ways of making these wafers. Now once you make this, you have to go for the second step, wafer production, which means you need to slice it and get wafers as we see here. So there's multiple sets of wafers. They are just semiconductors, discs. So you actually have to sew this first, like maybe trim the edges, similar to slicing something, right? So you use diamond-shaped, diamond-tipped saws because you need precision cutting. Still, it will be like coarse when you cut it. And so your gas, that's 100 micrometer thick or 50 micrometer. I can't remember. It's 100 micrometer, I think, gas, P1500. Now, when you actually cut this to wafers, it will be thicker than that, because if you handle 100 micrometer, it will be very flimsy, it will break, it will be brittle as well. So you'll probably cut it to like 600 micrometers. And so a company will make this and they will sell this to fab, possibly, or the fab might do it themselves. Now, so this molds to shapes by sewing off the ends, and then cylindrical shapes then sewn to wafers using saw impregnated with diamonds. Now, once you cut it from a saw, you will have a coarse surface, right? So you need to make it more smoother. So they do some chemical etching. And then once you do that, you get a decent surface that you can grow other layers. So this is just a substrate, just a gas substrate, that's it. Right? It's a semiconductor only. So that's the second step, wafer production. So these are common steps. It doesn't matter which process you use. If it's silicon, it could be silicon wafer. Now, so when it comes as a substrate, the substrate itself is just an insulator, if you think about it, because it doesn't have enough free electrons for things to, for the currents to flow. So you need to grow some active layers. Now that's called surface layering. Now there's different ways that you can grow active layers. So the one is ion implantation, or the figure shown in the top. So you actually have the wafer on the in here, okay. So this is done in the fab. So they have to dope the wafer so that it has enough either electrons or enough holes so that it can carry current, right? So this is a control process. So they have all the apparatus to make it more controlled and dope gas wafer or whatever the wafer enough so that it has a surface layer built on top of it. So these are the three methods. The idea is for you to go away and read about this stuff, okay, or watch videos. There's a lot of things to learn about it. Now, and then the ion implantation is one of the methods which is shown in this graph. So you actually provide an ion. So you extract the ion particles, then you filter it out, and then they come and hit the wafer, and there's a surface layer build up on top of the gas or whatever the substrate. Another method is molecular beam epitaxy. It's actually the wafer is on the top here, and then the dopants get shooted from these sort of guns to the wafer, and they get the active layer build up. Okay, so these are more like process how they do it, and we are pretty much just going off the surface only, right? Because and the third one is metal organic chemical vapor deposition, so MOC-VD. So they actually do some sort of a chemical reaction. So they provide gases, control gases. So one with, say, iron particles. Most of the time they do. They send some sort of a hydrochloride formulation with the iron particle, and then the ferrous get deposited, and then the chlorine gets away. That's the normal. There's probably more mechanical stuff than that. I'm just from my memory. So what you need to remember is that these are just three methods of getting an iron layer or doping the substrate. So once you do that in a proper controlled process, then you will have surface layers. So you have a substrate, and then you have a surface layer. So we came back 3 steps from the growth to wafer production to surface layers. Okay. Then this step is the most crucial step. Well, you need all the steps, but this is what's more important for you to understand in terms of layouts. Have you heard of photolithography, or have you used it before, or in any other subject? The photolithography is pretty much printing with light. Okay, so it's more like printing in any other surface as well. The idea here is, so once you when you guys make your tracks, right? So it's a metal one. So if you just use a PCB, what you do is there's different ways to make it. If you do a PCB, you can actually etch away any unwanted chemical metal, right? Then keep your tracks. Now here you can do it either that way, or you can just print the metal as you want. Now when you do it, there's 2 different ways to do it. what is called the etch process and lift off process. For example, just to get the idea straight, you can, so let's say you get the surface layer build up, and then you put metal on top of it, and then you put a, say you put a mask, okay, with a certain pattern. So it can be with your tracks covered. So if you have a mask with the track covered, and then you then put your photoresist substance. So put your substrate, metal layer, and then so you have a substrate and then a metal layer, and then you have a photoresist. So photoresist is when you actually expose that to light, it can make a pattern, and then you can wash away the rest. Okay, so when you have photoresist, then you put a mask. So once you put a mask, so if your tracks are there, so let's say this mask will cover that, this area. Then you light up the surface, and these things get scratched away. So you are left with something like the metal and the photoresist mask covered, right? Then you can wash away the photoresist, then you can have the two metals. So this can be your track. So that's called positive. So you can build up a lot of layers. So if you do fabric painting, you do the same thing. You have your cloth, put a mask, paint it, take it out, so you have a tracks, right? Same thing. Or you could first do the so this is one way. The other way is a negative etching. So in this method, you put the mask opening up your tracks, and then opening up your tracks and then flushing away the rest. So if you do positive etching, you get, say this is metal. These are your tracks. If you do negative etching, you will have tracks in these places. Now, you won't have perfect tracks, so it won't be exactly square shape. They can be having a positive slope. You know, on your substrate, your metal track can have a positive slope, or your metal track can have your negative slope. Also, there's a certain width you can go with this metal. So usually it's about 5 micrometers width. So that's what, when you have the layout manual, it says the minimum width you can do like 5 micrometers and all that. And you need to make sure your tracks, when you do your layout, is at least 5 micrometers or more. So you have to look at your layout manual, and once you do all your layouts, then you do something called design rule check, which is called DRC. And in the DRC, if you are lower than 5 micrometers, you'll get picked it up, and then they'll say there's a design rule error. Okay. Now the feature sizes like this depends on the light, wavelength of the light that you use. Now when you make a transistor, you have your source and your drain, and you have your gate finger. In the gate finger, if you look at that width, it's much smaller than 5 micrometers, right? And the gate fingers, you can't use the photolithography techniques to draw it. So the foundry has different sets of techniques. So they can do laser printing, the metal deposition. So it could be, so because your process is 0.15 micrometer width, so it's much smaller than 5 micrometer, right? So there's different techniques. So photolithography is a cheaper way. Okay, if you have to do optical printing of electrons in like a metal deposition, it's going to be expensive, so they only do it for the transistors. Okay, so as I said before, these are just indications for you to go on and read about this. So this is the main, so photolithography is something that you need to be very, like, read about it, watch videos. I think watching videos on this would be much easier, because it will show you like animated videos on how you print really different layers. Otherwise, it's sometimes hard to understand how the layers are built up. So in the photolithography, you can actually make either active devices or passive devices. So you build up from the bottom to top. So this is the substrate. And then you build up, so this is the substrate. You build up your metals, so layer by layer here. Now there's an order in which they are built. So you can use, so that's order. If you look at your iLearn, I think I uploaded the layout manual, I think I did there. So it actually tells you what is the fabrication sequence for the P15. So you make up your mesa layers. Mesa layers is more like a mask to cover up the things that you don't want to like put other stuff. So you want to isolate a certain area, you put a mesa layer. So there's P mesa and mesa, and you build up these P mesa and mesa, ohmic mesa. Now you don't really need to clearly understand details. You just need to know that this is how the photolithography works. Okay, because it depends on each process. Yeah.
So when you're building it up, are you just blasting with light right at the end, or is it one layer blast and another layer?
Blast. Yeah.
Right.
Yeah. So you do one layer, mask, last, maybe clean up, then another layer. So it's a longer process. But when you do a wafer, that's why when you make your circuits, you put all your circuits in one reticule, and then you'll have a mask for each layer, right? So in your AWR project, you can look at your layers. Especially when you go to layouts, you probably have to look at it. It will say all these names: P mesa, N mesa, say metal 1, metal 2, VR layers. So this is how you build up all these layers, and that's done through photolithography. So in here actually you will see, I'll go back to the bigger picture here. So you can make so this is actually a transistor here, and this is a resistor here, and this is a diode here, and this is a capacitor here. So the capacitor, if you look at it, it's much easier to understand. You have one or two layers. So if you see this on the creation of passive device, you'll notice there's a first interconnect metal and the second interconnect metal. So first interconnect metal is your metal 1, second interconnect metal is your metal 2. So when you make the capacitor, you will have your metal 1 on top of all other layers. You only need to worry about your main layers. Then you need to have a spacing. So you fill that up with set of a dielectric. So that dielectric can be high dielectric as a silicon nitride, because if you want to make a big capacitance out of it, because you need a high dielectric constant. If you want to make a low dielectric capacitor, you will probably fill it up with polyimide. And then you lay out your metal 2. So depending on your area, you will get the capacitance. So you will have to have a contact here. So that metal 2 will have to route out, and the metal 1 will have to route out, and then you need to have, say, contacts to other circuits. Any questions?
So the dielectric between the two plates,
Yeah.
is that decided by the designer, or is that decided by the fab?
Yeah. You can, when you get the PDK, right, you specify the length and width. It will calculate the capacitance for you. So it's pretty much the fab selects it.
So when, because I think we only had one in the beginning process, but will the fab sometimes give you different
No, actually, what they will do is they will just give you one model. So you will notice in the rules, they'll say the minimum and maximum you can go in terms of width, and you'll get a certain capacitance. And if it's after a certain level, they might not use the silicon nitride, they might use polyimide. You don't know that. That's the thing. So they'll control it in the process. Yeah. And then once you make a, so this is how you build up each of the components. Now you don't have to worry about how you build up all the layers. You just have to follow the PDK rules. That's it. So you make the PDK itself, when you pick a capacitor, it follows all the rules. When you connect each of the say in your circuit, you connect a capacitor to inductor, you have to route a metal one, right? Or a thick metal. So the other thing is about thick metal. I don't know whether I mentioned. So when you have a metal one in one layer, then you have a metal two in one layer, another layer. So in the P15 process. So by having that, we'll actually let you create air bridges. So when you have a metal one and when you want to cross over, you don't want to jump into each other, right? So you will, so let's say you want to make a circuit, there's a microstrip line like that, and you have a microstrip line like that. So you will stop metal one here, then you make metal two air bridge here. This part metal two. So when I look it from the side, I will have metal one, and then metal two air bridge. So to connect metal two and metal one, you need to have a VR. Okay, so you will notice, I will show some of these examples today. You will need to have the metal one coming in, then a VR, then metal two VR. Then it is like a air bridge. It will go over the other metal, right? So if it's two metal process, you can use air bridges. Some processors are three metal processors, so you can have three metal layers. Okay. What else did I miss? It's important for your E15. Other thing is thick metal. So this metal thickness, the metal one, determines how much current you can handle, because you can't, it's like a fuse, right? You have high current will blow it up. So you have metal one, the layout manual will say how much current it can handle actually. If you go to lab manual, right? Lab 2 assessment 2, in there's two PDFs, I think, or one PDF at least. I didn't? Okay, so then I should upload it then. Okay, I thought I have. If I'll do it today. So that layout manual will have all these descriptions. So there's a process manual and a layout manual. The process manual explains all this. The layout manual tells you the rules around each of the devices. Like it will say capacitor can't go below this width and length. Metal to metal spacing can't be less than 5 micrometers. Metal one strip has to be at least 5 micrometer wide. Things like that will tell you. So you can't violate those rules. Okay, it's just like that's the limits of the fab facility. If you make something like smaller than that, they will not go ahead make your design, or they might just don't care. They will go ahead and you don't know whether they made it right? So at least they'll give you a guarantee if you make it within their limitations, your circuit might work. So photolithography is that. I'm probably a bit rushing through because I want to cover the EM too, but this is all things that you guys have to read anyway. So once you make that, let's say you make up all your circuit, right? And then you have a thick wafer and then multiple layers on top of it. So you have to convert that way because your microstrip line widths, the width is determined for the characteristic impedance, right? So we covered characteristic impedance earlier. So for 100 micrometer thick, I have to pick, I don't know, 50 micrometer. What is it? Can you guys remember? What's the width of it? I think lab 2 we've we've used the right width. So for 100 micrometer thick, say we have to use 20 micrometer with metal 1. So if I don't make my wafer 100 micrometer and keep it 200 micrometer, my impedance drops, right? So the fab has to trim this wafer to the right thickness. So this is where you have all the layers. They'll put a tape or sort of like some gel material, and they will actually grind the other side. So you turn it upside down and grind it until you get the right thickness. Okay, so we don't have the, so the reason they want it 100 micrometers, so we could leave it at 600 micrometers. So it's thicker, it is much better, isn't it? Because if it's thicker, it's more it's very strong. You don't get brittle substances. So if, for example, indium phosphide, they make it on gas. You can't just make indium phosphide, it's too brittle. But there's a reason they want to still make it thinner. Is like if you have thicker substrates, you will create multimodes, which means you will not only transmit your signal in the microstrip line, it will also transmit along the wafer. Right? So thinner it is, that transmissions happens very high frequencies. So if you are in millimeter waves, you want it 100 micrometers thick at least. If you are in microwave RF, like say 10 gigahertz, don't mind 200 micrometers, because whatever happens at higher frequencies really doesn't impact you much. It might impact other circuits around you. So if you go for like 100, say terahertz range, like in the 100 gigahertz above, you might need even thinner ones, but really can't make much. You can only make 50 micrometers at the moment, thin. It's very hard to handle that material afterwards. So there are tricks around it. So the technology is much more advanced. This is just like scratching surface, okay? Now the last, not the last step, the one before is you have to make your vias. So if you have back vias, you guys have seen back vias, right, in the layout? In the transistor, you have source connected to the ground through vias. So the next step is to actually make the via and then make the back face metal. So that provides you the ground. So this is how, so if you want to make this connect to a via, you actually have to make the via connection. You drill it and then you put a metal layer that forms your ground. So once you have that, you have to make, so you will have multiple circuits here, and they will have saw lines, what you call the saw lines. So you need to actually cut each of those circuits. So you can either do scribing or sewing. So scribing, you make a small cut and then you break it pretty much. And the sewing, you can do a diamond saw and then to actually sew and separate your circuits. So I'll come back to that maybe because you guys haven't seen a final layout, might be confusing for you, like what I'm talking about. Maybe I should show you one of the final layouts. And so the other thing they do is quality assurance. They will actually make, when you make your wafer with other circuits, they will make some things called PCMs, process control monitors. So they'll put it in every wafer, and they know that characteristics, and they will measure it in every wafer. Because the wafer, you have a 6-inch wide wafer, right? And that wafer might have issues, you don't know. So you make PCM and compare it with the another wafer, and if they all seem very similar, they might think, okay, this is a good wafer. So, but still on the same wafer in different places, you might have issues. You don't know really, because your circuit might not work. You don't know if it's due to wafer. You don't know if it's due to design, right? So sometimes you place your circuits in different places of the wafer, just slight variations. Now, so that's the QA part.